Hi everyone, my name is Kanaga and this is MonoDepth, a self-supervised monoocular depth and ego motion estimation system that I built from scratch, largely using PyTorch for the computer vision course. So the word monoocular means a single camera and the word self-supervised means load labels. These two constraints together make this both an interesting and genuinely hard problem to solve, and I want to walk you through exactly how I went about this. So let me start with why this problem entered my brain and why I wanted to try to attempt to solve it. Autonomous vehicles need to have a clear understanding of the three-dimensional world around them to make safe decisions. This could be how far is the car ahead in front of me? How much room do I need to change lanes? How far is each pedestrian to guess when I need to apply brakes? So, the gold standard way for doing this is a sensor called a LiDAR. It fires laser pulses in all directions and like measures how long they take to bounce back, giving us a precise, sparse 3D point cloud of the environment. But LiDARs are pretty expensive. So the dataset that I used, called the Kitty dataset, which we will get to in the next slide, costs around $75,000, and that is the cost of that is well over the cost of most first-hand cars. Cameras, on the other hand, can cost under $100, and they're already on every phone, every laptop, every car, every modern car at least. So the question here is, can a neural network learn to extract this depth and in a depth map from a single camera image without ever being given a depth measurement to learn from? So we wanted to, or I wanted to not learn during the evaluation with the help of all of the LiDAR, but rather actually just train on raw video with zero depth supervision whatsoever. And that's exactly what this project does. So, before I get into the methodology and how I went about this, I want to show you what the system actually produces so we can orient ourselves and think in the direction of what the results are going to look like and how we might reach that. So, on the left, we have the raw RGB image from a car driving through what looks like a parking lot. On the right is what our trained model in the end predicts when you give it just this one RGB image. So over here, the color encodes the depth in meters. We can see a mapping of that on the left corner. So purple here is close and yellow is far. You can see that the road surface is like predicted as closest, and the trees and the buildings are like farther away. And within the trees specifically, you can see the trees in purple are the ones that are closer to us, and the trees in yellow are the ones that are farther from us. And you can also see the difference in the cars between cars on the right and the cars on the left. The cars on the right are a much deeper purple color, whereas the cars on the left are like a hazy lavender color because the left parking lot cars are much farther away from us. So this sort of gives us an idea of exactly what the prediction in the end is going to look like in terms of number of meters and the color coding of it so we can orient ourselves to it. So model over here is predicting this depth in layers and meters over here and giving us a depth map, learning purely from just watching a video. Now, going back to the data set that I mentioned earlier and the LiDAR. So, the data set that I train and evaluate on is the Kitty Vision Benchmark Suite. This is collected by Karlsruhe Institute of Technology. I hope I'm pronouncing that right. So, they drove a car with a sensor suite on the roof, which is four things for us. So, a pair of cameras for stereo color, then the Velodyne radar that I had mentioned earlier, which is sort of spinning and calculating it from all angles, and we have a GPS with like inertial measurement. The camera over here, the camera pair, gives us outputs in 1392 by 512 pixels, which sort of gives us this like vertical image, which we saw earlier, as opposed to generally what we would see in like a 9 is to 4 ratio or a 16 is to 4 ratio. And the camera gives us outputs in 10 frames per second. So the standard protocol from everything I've seen done, especially within, like, let's say the MonoDepth 2 paper or any other paper that like does work with the Kitty Vision data set, is to use a split of the data set called the eigen split, which is named after the researcher who did establish the eigen split. According to this, the training set is 35,436 image triplets. Triplets over here is we get three consecutive frames from the same sequence, which would be like IT minus one, and IT plus one. So we get this across 4 to 6 different driving sequences. The test set is not triplets but discrete frames, and it is 372 discrete frames. And these have been like hand selected by the researcher, Eigen, as mentioned earlier, to sort of cover diverse, different kinds of scenes. So for each test frame, there is like a corresponding LiDAR scan that we can use as ground truth to measure our predictions against in like the final testing. The critical point, again, the one that I want us to note, is that during the training, we never touch this LiDAR data. We train purely on the RGB sequences, and the LiDAR only appears at the evaluation time, and it is only there to tell us how accurate our predictions themselves are. Okay, so now let us look at how the system works. There are three major components here. So the first that I want to get into is the depth network. It is the blue block. It takes the current frame. I'm going to going forward. I'm going to call it IT, or target frame, and it gives us as an output the prediction of how far away every single pixel is. The second blue block that I want to talk about is the post network. So it takes two consecutive frames, the target frame and neighboring source frame, and predicts how the camera has moved between them. So the prediction here is not in GPS coordinates, but rather I'm going to be getting a rigid body transformation. So a rotation and a translation that happens in 3D space. The third component, which is in yellow as a block, is the inverse warp. So this is not a neural network, unlike the depth and post network that we saw earlier. This is just geometry. Over here, within the inverse warp, we take the depth prediction and the post prediction and the camera intrinsics. So using these three, we synthesize what the target frame should look like if you start from the source frame and apply the rigid body transformation. Uh, so with that, we're trying to predict the camera motion, and we synthesize a frame from this called IT prime. So then we finally have the loss function, which is a red block, which compares IT prime against the real IT. If the depth and the post predictions were both perfect, these two images should be identical. The difference between them is the error signal that we do back prop and get the gradients off, and it goes through both the networks. So that is the entire training loop. We don't use the LiDAR, there are no depth labels, it is just geometry and like consistency between the video frames. Okay, let's go deeper and look at these individual networks themselves. So first, I want to get into the depth network. The depth network actually uses a ResNet 18 encoder, which is pre-trained on ImageNet. And over here, it has 5 stages, as we can see, a stem convolution followed by several residual blocks. So each stage in the encoder halves the spatial resolution and increases the number of feature channels, because that's what convolution layers do. So by the time I reach the bottom of the encoder, the feature map is 32 times smaller than the input, but has 512 channels, which encode like rich semantic information that is present in like the scene. And then we go to the decoder side of it, which reverses this process. So at each stage, it upsamples. So you have con2 delays, which like upsample them by a factor of 2, and concatenates also the corresponding encoder feature map via the skip connections. So those are the dashed horizontal arrows we can see. So the skip connections are critical over here because they carry these the spatial detail, the fine spatial detail that we get in the early encoder layers, that like by the time we come to the decoder layers, they could have been lost. So without these residual connections, the depth maps would be blurry and spatially imprecise. So at each decoder stage, we also get, if you can see in green blocks, disparity maps. So that gives us 4 predictions at like 4 different resolutions as we upsample. However, all four of these get upsampled to full resolution before like the loss is computed. Next slide. Post network. The post network is a little simpler than a depth network. It takes two stacked frames, that is six total channels, and runs them through six strided convolutions. These like compress the spatial dimensions. Then we have a global average pool, which collapses this entire spatial structure into like a single 256 dimension vector, from which we get two branches. So first one is the translation head, which predicts translation as three numbers, and the other, which is like the rotation head, which predicts the rotation as three numbers in axis angle form. Now we convert this axis angle form into like a proper like rigid transformation matrix using the Rodriguez rotation formula. So then using these, we put together a matrix, and this is what gets passed into the inverse warp. Okay. Now let's go into the inverse warp. And let's go through these explicitly because this is the mathematical core of like exactly what happens within the system. All of the other parts just produce what goes into this. So pretty slowly, let's go into it. The first one is let's go into it step by step. Unprojection, the first step. So for every pixel in the target frame, we have like a predicted depth value d. We form a coordinate vector, which is the pixel's x position, y position, and 1. And we multiply it by the inverse of the camera intrinsic matrix K, so K inverse. This converts it from like a pixel space into a unit ray direction in 3D camera space. So scaling that ray by the depth d, again as you see, so we have the uv1 multiplied by K inverse. Now again, we're scaling it by the depth d. So that gives us the actual 3D location of the pixel in the world as seen from target camera. And that is what we mean by ego motion from target camera. Now, step two, the rigid transformation. The post network gave us like a 4 by 4 transformation matrix T. So we multiply our 3D point by T, every 3D point that we calculated in the previous step. And we express it in the source camera's coordinate system rather than the target camera's coordinate system. And we get P target from there. Next step is the reprojection. So now we have a 3D point in the source camera space. We divide it. We divide the x and y coordinates of it by the z coordinate. So that's called the perspective divide, and this accounts for like the fact that things that are like farther away appear smaller. And so while dividing it, we do the perspective divide and account for that. Next, we multiply by K, the intrinsic matrix of the camera, to convert it from camera space back into like pixel coordinates. So this tells us where in the source frame that 3D point appears. So 3D back to 2D over here. And you can see that gives us like U prime, V prime, and 1. And also the division step in the formula. And final step is bilinear sampling. So we normalize these pixel coordinates to range -1 to range +1. And we use bilinear interpolation to read off the pixel color from the source frame at that location. So differentiable over here means like the gradients can then flow back through back propagation and through the whole sampling operation all the way to both the depth and the post predictions. So for the rotation specifically, we use the Rodriguez formula. So this converts the axis angle output of the post network into a rotation matrix. This avoids something called the gimbal lock, which is a singularity problem you get with like Euler angles when two rotation axes align. Next slide. To go into the architecture one at once in one place that we just went through to summarize what happened here. The depth network takes a single RGB image and produces disparity maps at four scales. The disparity is the inverse of depth. We predict disparity rather than depth directly because disparity is bounded between 0 and 1, which makes it easier to like regress. Uh, so we convert this to metric depth by taking the reciprocal because it's just an inverse with calibrated minimum and maximum depth bounds. The post network takes a concatenated frame pair and produces a 6 degree of freedom transformation, which like three translation parameters and three rotation parameters in axis angle form. We scale this output by zero point zero 0.01 at initialization. This keeps like the early predictions closer to identity and like stabilizes the first few epochs of the training before like the depth network kind of has learned anything, because the depth network is slower to learn than the post network is, because the depth network has a harder job to do than the post network does. The inverse warp. So this implements the four geometric steps that we just went through. Then finally, we have the loss, 85% SSIM and 15% L1 at every decoder scale. We had four scales. And we also have auto masking, which handles dynamic objects and static camera frames and is edge aware. And we also do smoothness regularization. Okay, now this is another slide I kind of want to spend a little more time on, because this was something I built from scratch, and that meant a lot of problems and solving each of the failure modes that I went through. So the first one was the multi-scale gradient disconnect. So, according to most of the papers I read, and more specifically MonoDepth 2, we compute the photometric loss at four decoder scales, as we had seen earlier, and this gives the network richer supervision. So, what I initially implemented was computing the warp once using the full resolution depth map, and then reusing that single set of warp frame for all of the other like disparity maps. So the problem that happens here is that the three lower resolution scales actually had no connection to the photometric loss whatsoever, and the only gradient they received was from the smoothness loss. So, and the smoothness loss like trains the network to just give us like flat images, flat planes, because the depth map is constant and has no gradient, and therefore it's no smoothness penalty. It was a pretty easy fix over here, just to loop the inverse warp operation at like every scale instead of just at the topmost, most the one with the highest resolution, and to do it independently. So every decoder layer receives like a direct photometric gradient corresponding to it, and this kind of like really stabilized my network and took my absolute relative error from like completely unstable down to like 0.14, which was pretty good. The second issue was a collapse of the resolution within the decoder layers. What happened there was the decoder was outputting depth maps at 96 by 320 instead of 192 by 640, which is what we would expect actually. And this was a mistake in actually the upsampling. I had a scale factor of 2, which relies on integer arithmetic that like kind of like rounds it up for like non-power of 2 dimensions. So I just had to replace it with like an explicit target size matching the encoder skip connections and like the spatial dimension that comes out of it, and that like fixed this immediately. So the third was a mismatch in the pixel space. So the ImageNet normalization transform shifts the pixel values from 0 to 1 into like -2 to +2, with like a specific mean and like a specific standard deviation. My what frames were like normalized in space, but my target frames were like in raw RGB images, so raw pixel space. So the loss function was computing tensors in like very different numeric ranges. They weren't bounded in the same range. And this produced gradients that like pointed in the wrong direction. The fix again was pretty simple, just like like explicitly reverse the normalization on the source frame before we warp them. And the fourth and fifth one over here is like handled by the auto masking and the smoothness loss. So dynamic objects like moving cars violate the static world assumption and get suppressed by compressing the warped error against like an unwarped baseline. And textureless surfaces like blank walls and like roads, they got regularized by the edge awareness smoothness filter that we put in, like the smoothness term. This like downweights everything, and the smoothness penalty at the image edges is also downweighted, so sharp depth transition at object boundaries had to be preserved that way. Okay, now getting into the results again. Once again, we can see this was the very first result we saw. More that shows which building is close by, which building is farther away. The cars on the road are at a lavender haze, which is slightly far away from us, giving us like an understanding of how far that might be. Again, we can see here which trees are closer to us versus which trees are far, which cars are like extremely close to us, very dark purple, versus ones that are pretty far away, sort of lavender. Okay, now That was quant yeah, those were like qualitative results of like what we can visually see, but we in machine learning we really like quantitative results. So let's get into like a little bit of that. So these are the standard eigensplit evaluation metrics. So the first one is the absolute relative. So this measures the mean absolute relative error between the predictions of our model and like the LiDAR's ground truth depth map, pixel by pixel. So the absolute relative error I got is 0.137. Just to put that in perspective, MonoDepth 2, which is like the Google DeepMind paper that has established like most of the techniques that I've implemented here, it gets on this exact same benchmark, achieves an absolute relative error of 0.115. That's only a 19% gap. The next one would be RMSE, root mean square error. So that is of 6 meters. So what does this mean? The average absolute depth error across the test set is 6 meters. So for scenes where I have a range of like 5 to 80 meters, that is a pretty reasonable result, especially for like a from scratch implementation. And I only trained this for like 70 epochs on like a single 800 GPU. One other metric I really want us to pay attention to over here is the delta, delta less than 1.25. This metric kind of tells us what percentage of pixels have a depth prediction within 25% of the true LiDAR measurement. I was able to hit 83.7%. What does this mean? More than 4 out of 5 pixels in any given test image are within a quarter of the true depth value using only a camera and no labels at any point during training. And that is a result I'm actually pretty happy to have received and achieved. So this was a project done by me alone. I'm Kanaga. If you have any questions, this is my email ID. Please feel free to contact. I would love to discuss more about this project. And I really enjoyed having taken this class and gained the knowledge to be able to work with 2D to 3D projections and find what depth maps really can do for us. Thank you.